Good morning, all. I welcome you for our last webinar of the series, which is on tensile and high temperature nanoindentation in scanning electron microscope. On behalf of Industron and Bruker Nanosurfaces, I certainly thank for all the participation that we have seen in this entire series. It's been wonderful to see such participation for this kind of technique that we have demonstrated in the past webinars. Before we commence, I also would like to mention that all our participants will be in listen mode only. You'll definitely have the opportunity to ask questions at the end of the talk. And should you face any problem with respect to your audio or joining, please let me know. You can drop me a text or email me. So without further delay, I'll introduce our today's speaker. So Dr. Syed Asif, he's currently Director and of R&D in Industron Nanotechnology Private Limited. He's based in Minneapolis in US. He's graduated with his PhD degree in material science from University of Oxford. And he did his master's in mechanical engineering from Indian Institute of Science in Bangalore. So he has basically 30 plus years of experience in designing and developing these nanomechanical test instruments, and certainly has been a key player in developing all these nanomechanical test instruments with Bruker Nanosurfaces. He has over 120 publications and 22 active patents. He has also won 4 R&D awards. So without further ado, I would like Dr. Asif to take the stage and deliver today's lecture.
Thank you, Pratyank. Thank you for the introduction. I'm going to take the video off because of the bandwidth. And welcome everyone for this webinar series. Today will be the last part of the series where we'll be covering in situ nanomechanical testing, but mostly on an ACM. Just to recap, in the first webinar, we covered the basics of nanoindentation. And in the second webinar, we covered dynamic mechanical testing at nanometer length scale. We also looked at the high temperature mechanical testing in combination with the dynamic nanoindentation. In the third webinar, in the last webinar, we covered about nanomechanical testing inside a microscope. I covered most of the time on transmission electron microscope. I did cover a little bit on the SEM. So in today's talk, I'll be talking more about the in situ SEM-based nanomechanical testing, and we won't have time to cover Biosoft. I think if anybody is interested in understanding what is Biosoft and how we can do nanomechanical testing in combination with the biological microscope, there are videos in our website. You can have a look at it. So today's talk will be predominantly on the SEM-based nanomechanical testing. So without delay, I'm going to go for the next slide. You can see the TM-based picoinunders. You have multiple.
Dr. Asif, we are not seeing your slideshow. It's.
I'm sorry. Now?
Yeah, have the it's fine. Yeah, it's good.
Oh, yeah, very good. So on the TM-based picoinunder, we have for all the microscope that you have in the market, whether it is a Geol, Hitachi, or FEI, we have the holders for that. I pretty much covered most of it in the last webinar. For the SEM picoinunder, we have 2 models. So one is PI85L and another is PI89. PI89 just came out with maybe about a few months ago, like maybe 5-6 months ago. And both of these models are available for all the microscopes, whether it is Hitachi or Geol or Tescon. And then there is a significant difference between these 2 models. When I have time, I'll cover that. But importantly, what this system has is basically a transducer. A transducer is mounted on a fracture-based stage, which has an internal sensor which measures the displacement as you move the transducer. This transducer is a modular design. And these stages, there are about 1, 2, 3, 4 linear stages and 2 rotary stages. I will be showing that in the next few slides. These linear stages, they have encoders about 1 nanometer in resolution. This is a robust mechanical design. They are very stiff, so have very high stiffness. For mechanical testing, you need to have very high frame stiffness. And this whole system can be mounted in an SEM. And I think I have one slide to show that. So let's look at how this whole arrangement is done with this frame. Like I said, the base is basically a closed loop flexure actuator, and it has about 150 micron displacement range, and we have a pretty nice high resolution capacitance sensor detecting the displacement. So the maximum range is about 150 micron. On top of it, you see this transducer, which is sitting on top of it, and then you can see the transducer end with the transducer tip, which is the diamond tip that we use normally for doing mechanical testing. And the transducer inside, there are 2 varieties of those. One is the active one, which is a 10 millinewton capacity transducer, which works on electrostatic force actuation principle that I covered in the first webinar. Okay, so this is shown here schematically. The flexure is something that has been actuated with the piezo actuator, which is supported by a spring. And then the displacement of this flexure is being measured by this capacitance sensor, 3-plate capacitance sensor. That's the sensor 1. And this transducer is mounted on this flexure. And this transducer has a couple of transducers. One is the sensors. One is the displacement sensor, and which measures the displacement of this spring. In second arrangement, you can also have an active transducer, 3-plate capacitance transducer, which can actuate through electrostatic force actuation mechanism. So with this combination, we have 3 different control loops. One is open loop, the displacement control, and load control. Because we have 2 types of sensing capability, active transducer to apply the force electrostatically, as well as the passive sensing through a spring deflection, you can have this combination as well. So there are about 2 times 3, about 6 combination of control loops possible with this particular system. So it's very flexible, very modular, and you can think about any type of experiments that can be done. You can do high standard experiments, you can do creep experiments, you can do fatigue, DMA type experiments. All of those things are possible. Okay. So in this slide, I'm kind of just showing this transducer with electrostatic force actuation. You have 10 millinewton capacity, 30 millinewton capacity. And with the passive spring-based sensor, you have 500 millinewton capacity as well as up to 3.5 Newton capacity. Okay, all this combination can get up to 150 micron displacement capability. Okay, so then for the high load capacities for 500 millinewton and 3.5 Newton, the piezo actuator, that is the flexure actuator, is the main mechanism of actuation. So okay, so with that. And this is what I mentioned, that how this is mounted inside a electron microscope, scanning electron microscope. You can see the electron gun and then detector, and then it is mounted at an angle so that you can have this full view of this tip when you do these experiments. This is a very small system. It weighs about 600 grams, and it can directly be mounted onto the SEM stage. And in the SEM stage, you also have other detectors called the EBSD detectors or some other EDS detectors. In combination with those, and then with this transducer, you have full potential of doing mechanical test as well as doing this analysis of the EBSD or EDS analysis of your sample. And like I said, it is available for all the microscope that is available in the market right now. Okay, So on top of it, these linear stages, which are useful for positioning the sample as well as positioning the transducer. You also have a rotary and tilt stage. This is the rotary stage, which can rotate in this axis. And the tilt stages move in this tilt positions. And you can also mount this in other way around so that the rotary axis is along the axis of the tip. So it can have that combination for certain type of experiment. So it is very flexible in that way. So I think that next slide will show you probably a better picture of it. Basically, the rotation is in this axis, and then the tilt is on this axis. And the main purpose is I'll be showing a couple of examples where you can use this tilt and rotation stage to go and do sometimes if you wanted to understand the anisotropic behavior of your sample, mechanically, you can do that by rotating this sample and doing this indent at different orientations. You can also use this rotary and tilt stages so that you can position the sample for the EBSD or EDS detectors so that you don't have to take this whole stages and the system out to do that. So in situ within the SEM, you can go and look at the sample with the EBSD or EDS detector and analyze the sample. At the same time, you can bring it back and you can do the mechanical testing. So this video shows the tilt actions, and you can see in this video that's the rotary action. In this case, the rotary and the rotary action is along the axis of this cylinder. Okay. So quick two examples. I mentioned if you want to understand the anisotropic inundation behavior, this is an example for that. It's a calcite. And it has crystallographic orientation, and then orientation dependent deformation you can see by rotating the specimen at different angles and doing the indent. You can see sometimes pile up at particular crystallographic orientation and sometimes no pile up at certain crystallographic orientation. That shows the anisotropic deformation behavior of this material, and that can be studied with this type of arrangement. Another possibility is like when you do experiments on pillars, which are like when you do the experiments, you also always look at one particular view. You won't see the backside of it. With this rotary stage, you can rotate and see the deformation at different orientations. That is also useful, very useful. The third use that I haven't put here, but for example, like when you do the pillar compressions, sometimes it is very difficult to align the pillar along the axis of the tip. So sometimes this rotary and tilt stages are useful to align the pillar along the axis of the tip. So even for compression, pillar compression, this is very useful. So this 5 axis of 5 degrees of freedom is very important, and it is very helpful in doing experiments inside the SEM. Okay, so with these combinations, you can do nanotribology. I'll be showing in 1 or 2 slides on that. And with a combination of high temperature testing, you can go up to 800 degrees C, and I think 1000 degrees C is already available now. And you can also do, I'm going to cover all this thing in the next few slides. You can do accelerated property mapping. You can do SPM imaging. I am not going to cover that. It is basically a scanning probe imaging that I presented in the first webinar. You can do that inside the SEM. You may ask why, because in SEM, what you see is the 1 dimension, the 2-dimensional image. If you wanted to get a 3-dimensional image, it is nice to do this SPM imaging. Electrical contact measurements, I will be showing some examples of that. Direct pull tests, if you can fib your tip to do this, we can do that. Push to pull device to do this tensile test, I'll be covering that in 1 or 2 slides. And you can also, along with the electrical test, you can do that. And then nanodynamic fatigue test, similar to DMA that we do, we can use the same DMA concepts to do some oscillatory force onto the sample and understand the fatigue behavior of the material. And then in combination with EBSD, TKD, or STEM capable SEMs, you have a direct analysis of your material or a microstructure, and you can directly correlate that with the mechanical property. So all this is possible with this instrument. Okay, so now one example that I mentioned is to understand the grain orientation. In this particular case, nanoindentation is to measure the hardness and elastic modulus of individual grains. You can see the grain here, and you can see the grain, as well as you can also orient the tip if you wanted to rotate and orient the, for example, if you use a Knoop inender or a Berkovich inender, rotation of this inender tip will change the crystallographic orientation response. If you wanted to understand that, you can do that. You can also get the EBSD map to give the grain orientation. So now you know what the orientation of the grain is, and then you can also orient your tip in a particular angle and understand the mechanical response if you want to. And after the plastic deformation, for example, I think I have one example where you can start to see the grain boundary, the plastic deformation at the grain boundary through the EBSD image. I think this is another example where this is for a duplex steel. You can go and take the EBSD image of the steel to identify the austenite and ferrite faces, and that can be easily labeled austenite and ferrite faces. And then you can go and position the tip to do indents on those particular grains so that you are confident that where you are doing the indent for that particular face. And then you can measure the properties. In this case, that I'm showing the elastic modulus as well as hardness of the austenite face and ferrite face. You can see that ferrite face has higher hardness compared to the austenite face. So you can do all of that pretty neat metallurgical work, structure property correlation inside the SEM. I mentioned that you can see that here also you can see the local orientation spread map shows a preferential plasticity at grain boundaries. You can see the grain boundaries, you have much higher plastic deformation in this particular case. So it's very useful to understand the deformation behavior of materials with respect to different microstructures and phases. So with that, we can go and study on a number of materials. This is for this is a particular material where you have a high entropy alloy, and you can see multiple phases, and you can see at different phases that the mechanical response is different. And instead of doing at one place and understanding the response one phase at a time, what you can do also is using this XPM technique that we developed, where you can do an array of indent in a matrix of indent, and then you can get the mechanical property, and you can do this very fast. For example, you can do 5 indents per second, which means that it is a very high throughput experimental technique where you can do thousands of indents in an hour. In fact, actually, our colleague has done millions of indents to get a pretty nice map of property distributions on some specific alloys. So in combination with the EBSD, it is very useful. I'm going to show one slide on that, where you can go and measure these properties, and you can map them, basically how the properties distributed over an area. And then EBSD maps will give you the grain orientation or the crystallography, and then you can do the structure property correlation pretty nicely. And another important aspect of this fast indentation is when you do high temperature experiments, you wanted to spend very less time between the tip and the sample in contact. The faster you do, you have very less time in contact. So which means that you can reduce the interaction, and in many cases, like for example, you can avoid the tip wear if you want to, and also it gives you a very fast response of the material. So when you do these high throughput experiments, we found that by doing that, particularly for high temperatures, this is very useful. And you can do, because you don't need to wait for the material to stabilize for 30 minutes, 40 minutes. You can do experiments like thousands of experiments in 10 minutes. And so the high speed experiments are very, very useful. Especially for high temperature applications. So in the next slide, this is the example that I mentioned. In this particular case, the spacing between the indents are about 500 nanometers, and the maximum load applied is about 400 micronewtons. So it is constant load. and there are about thousands of indents done. And this is the harness map done through the indentation technique. And this is the EBSD map. You can see the grain orientation, as well as you can also, with the EBSD inverse pole figure map, you can see the high angle grain boundaries. These blue regions are high angle grain boundaries. If you look at the harness, you can see that the harness is very high for these high angle grain boundaries. So by overlaying this map on the EBSD map, you have a direct structure property correlation. And then you can do this for very high resolution. Even less than 500 nanometers is possible because we have the piezo's which are capable of moving up to like with the resolution about nanometers. So if you want to reduce the gap, you can reduce the gap. Only catch is basically when you do these experiments, you need to be aware that the spacing between the indents are determined by the deformation zone. When you do the indentation experiments, there are two types of zones. One is I covered that in my first webinar series. One is the plastic zone, which are very small. They vary in stress as a function of 1 by r squared, 1 by r cube. But then you have an elastic zone, which is much bigger. Okay, so when you do this gap, the distance between these indents, you need to make sure that they don't overlap. Okay. For example, if you are interested only on the plastic deformation, the plastic characteristic of the material, you can come closer and closer. But if you are interested in understanding the elastic properties, you need to keep certain distance. That is very important. So you have to be very careful what the gaps are. I mean, the system has the capability that it can bring as close as possible, but it will interfere. One indent will interfere with the other indent. So you need to be very careful about what you're doing when you do the interpretation of the results. Other than that, you don't have any much of restrictions. Okay. So this is the one. I'm not going to show much of compression experiments. We can do a lot of pillar compression. I think I will show one example with high temperature. And towards the end of my talk, we are going to show a video demo, which was done by our colleagues at Bruker. I'm going to play that. That will have pillar compressions. So I'm not going to do pillar compression. I'm not going to show the pillar compression. This particular thing is very interesting, mainly because this shows two things. One is compression of a particle, and at maximum load, you can hold the load, and then you can do the oscillatory load. And this is for a silica particle, and this is done inside the SEM. And this is kind of a small cycle fatigue experiments. The only interesting thing that you can watch is basically this silica particle is a glass type. It's a brittle material. You can see the plastic deformation, the extent of plastic deformation. The amount of strain that the particle can take is pretty high. Even some cases that we found that you can compress this material to a kind of a pancake. So it's possible. We found that it is only possible when you have the electron beam. In the presence of electron beam only, you can see this high plastic deformation. As soon as you switch off the electron beam, it becomes brittle. So the electron beams induces some kind of a deformation mechanics within the material that allows the material to be highly plastic. So one clue is that we can use this technique if you wanted to shape brittle glass materials like silica. You can do a high plastic deformation in the presence of SEM, an electron beam, to any shape that you want. Okay, so this is a pretty nice example. And this is for bulk metallic glass. There's a lot of work has been done in bulk metallic glass. And the important part of it is basically to understand the deformation mechanics. Unlike metals, they undergo a deformation through shear bands and shear-based mechanisms. And you can see that when you do these experiments, you can see this low displacement curve. The first low displacement curve on this material is the same material. You do one indent experiment, compression experiment, you can see a huge jump. At what it indicates is basically there is some shear deformation happening, and then you can do you can re-compress on the same material. You can see the small jumps. Each jump corresponds to the shear band formation, And I don't have the video, but in the video, you can directly correlate this jump to shear band. And you can see also this shear is happening at 45 degrees. And there are some secondary slips you can see at some other angles. So this is possible by directly observing it inside the SEM. Okay. And then finally, like the whole talk is about doing tensile type experiments inside the SEM. You can do this by two ways. One is directly you modify your indented tip in a way that it is kind of a hook, where you can flip the specimen also in a dog bone shape, and then you can pull this material. That is a direct pull experiment, and it is pretty expensive to do that. And so instead of going that route, you can also do in a very simple way. So we developed this tensile testing push to pull device. Just give me a second. I'll be back in a minute. I'm sorry, I had some noise disturbance, so I need to cancel that. Anyway, so this is the PTP device. What it means is it converts push action to a pull action. I think I covered that in the last webinar. I'll go through it again. What you can see is in this particular image, you have one structure which is mobile, and it has been supported by 4 springs. You can see the springs over here. And the other part is basically it is fixed. So when you apply a force here, it is going to move in this direction. So if you have a gap here, in this gap, if you put a sample and somehow you anchor the sample to these 2 ends, one to the fixed end and one to the mobile end, then you can convert this pushing action into a pulling action that will allow you to do the tensile experiment. That is the whole purpose of making this particular device. This is a patented device. By changing the spring stiffness, you can have a different systems for different things. For example, if you want to do high bandwidth experiments, you need to go for a stiffer springs. If you don't worry about, if structures are very thick and bigger, you can go for a smaller spring stiffness. For example, nanoscale wires and things like that, they are very fragile. So even like moving the sample from one location to another location may break the sample. In that case, you'd want to transmit only very small amount of vibration to the sample. So you prefer to use this higher stiffness springs. So what you can do is you can mount the sample. For example, you have one gap which is about 2.5 micron. You can also have multiple gaps, where within this gap, you can mount the samples. This 2.5 micron is plenty for nanoscale testing. And then you can do this tensile test, okay? So this you can do inside the TEM. I think I shown a couple of videos last time. You can do the same experiment inside the SEM as well. Okay, this is one example where you can go and pick the samples. These are all nanowires, molybdenum alloy nanofibers. You can pick them to your manipulators, bring them, and then put them. And then if you're using platinum welding technique, you can anchor the specimen in between the gap. And then you can apply the stress. You can see this a linear response, and then you start to have a plastic deformation. I'll be showing a couple of videos that explains this behavior, okay? Here is the video. This is for this alloy fiber. And this is for a case where you have only, you have 15% strain. You can see this insert shows the stress strain response. This is two stress, two strain response, because we know the geometry from the load displacement curve. We can convert that into the stress strain response. I'm going to play the video and I'm going to show that slowly. Okay, you can see this linear response is almost elastic. Then you start to have this plastic deformation. When that happens, you can see a lot of dislocation motions, necking of the material, and then and finally it may break. Okay, this is for a material which has about 15% pre-strain conditions. Okay, so again, like I can show it again. You can see that it's a linear response. And then when the plastic deformation happens, you can see the response is different. And then you can see a larger deformation happening in the material. Okay, this is with the pre-strain of 0%, but there's already pre-existing dislocations in that particular area. And I'm going to show this video again here. You can see the low displacement response. It is elastic, predominantly elastic. And then you start to see this dislocation motion and plastic deformation, necking and deformation. This is the video that this is the slide that I showed in the previous slide. So the entire thing was shown here, basically the necking and plastic deformation. Okay, so now if you have a dislocation-free region, if you do the same experiments, let's look at this video. Again, you can see this elastic response. Okay, nothing is happening. This area is dislocation-free. Nothing is happening. And then you reach to a maximum load. Boom. There is sudden nucleation multiplication of dislocations, and then the whole thing just jumps. Okay, this is when you don't have a dislocations, you nucleate this dislocation when you reach certain stresses. That's why you have this huge sudden. So these things you can directly observe. You can do the tensile test inside the SEM or TEM. You can directly observe what's happening to the material. Okay, this is another example. This is a gold film deposited on the PTP device. You deposit this thin film by any depositing technique, and then you kind of remove the material and only have material in the gap. Now what you can do is do the same tensile experiments. This is a thin film, and with the EBSD detector, this is done inside the SEM. With the EBSD detector, you can go and look at the grain orientation at different percentage of strain, and then you can correlate this stress strain response to the orientation change of orientation or rotation of the grain or growth of the grain. You can directly see that through the EBSD detector map, and then with that you can correlate the mechanical response directly. Okay, and I have a couple of, I think I may have one more, I will show that later, with the TKD detector, which is similar to EBSD. And along with that, you can, with this push-to-pull device, you can also do some electrical tests. For example, we have PTP, basically electrical PTP device, where you can put this nano, for example, if you have a piezo wire, nanoscale wire, you can put that, and then you can connect that with these 4 probes, and we have a fixed gaps. We know what the gaps are, and the 4 probes are very useful to, if you are trying to measure the resistance, you need to null the resistance of the probes. That's why you use this 4 probe method. And using this technique, not only you can do this mechanical deformation, but you can also electrically characterize that. Okay, so this is the PTP device again, and it has been connected to the external wall. And this is a pretty a nice development that we have, and you can do electrical characterization directly with this. I think I'm going to show one more video here. This is a zinc oxide piezo wires. And like I said, this has been welded through platinum, and you have connections, 4 connections, and applying a voltage, you measure the current, or apply the current, you measure the voltage. In this particular case, because this is a piezo wire, it's piezoelectric. If you apply a current and you can switch on and switch off, you can create a stress that you can sense through the transducer that has been plotted over here, and you switch on and switch off. And this is the voltage that you apply when you do that. Okay, or what you can do is you can apply a stress and measure the resistance change. In this particular case, you can strain to a particular strain rate, and then this is the load displacement response and true stress true strain response measured from the load displacement response, and this is the resistance change as you pull the fiber. You can do that. And you can also do at maximum load, you can keep the load constant, and then you can change the voltage and measure the resistance, measure the current. I mean, by that way, you can also measure the resistance as a function of different strain. So apply the load, keep the load constant, do a IV sweep and measure the resistance as a function of strain. You can do that. Okay, so this is what is been shown in this particular video. This is using the nano wire, and you can see in this video like the length is increasing as you apply, and then it is completely elastic. You can see this red curve is the load displacement response. It's totally elastic. You can see it is a retracing curve and not any plastic deformation. This blue curve is the resistance that is being measured during this exercise. So with this, we are able to measure the change in resistance as a function of strains, which is very useful for understanding these one-dimensional materials. Okay, and then this is the final example with this EBS. This is not EBSD detector; it's a TKD detector. It's a transmission frequency diffraction experiment. This is somewhat similar to see EBSD is this particular case, the material has to be transparent. So it is almost like a EBSD, but it's a transparency EBSD. So the material needs to be electron transparent. And then because of that, and we need to have a special arrangement, we have adapters for that. So if you have a TKD detector in your SEM, we can have this system, and then you can do this high resolution, similar to EBSD, you can do much higher resolution understanding of grain, rotation, orientations, plastic deformations. So this is what has been done in this next slide. This is on a thin film, and this particular case, this is from one of our customer who has done this experiment. And in this case, that you can apply at different loads to a different strain. You can do this frequency diffraction patterns at each particular loads and strains. You can see I was able to see what's happening here, not able to see. It's very difficult to identify what's happening unless you have a software that detects the changes. If you look at here, basically, after failure, there's a big growth in the grain, which is small here. You can see this small changes. So this is very useful if you wanted to do this structure property correlation. You can do this directly with the high resolution TKD detector. Okay. So finally, you can use this device to do some tribology. For tribological application, we have a transducer that directly couples to this tip holder. And this transducer measures the lateral force, and this transducer applies the normal force. And to apply the lateral force, what we have is a scanner, is the XY scanner, which can move in both X and Y direction. This scanner has a range of about 20 millimeters to 20 micron. This is not millimeter, sorry for the typo, 20 micron to 80 micron scan range. So if you put a sample over here, bring this the whole stages closer to this, and then apply a normal load through this flexure actuator, and then measure the lateral force through this lateral force transducer. That is what has been shown over here in this particular case. With a normal load, you apply the load, and then you started to slide. Then you can see this at some load, at maximum load, you start to have these delaminations that you can see from this load drop, both in the normal as well as the lateral forces. That kind of gives you the critical load that requires to remove this thin film from the surface. And from that critical load, and with the proper modeling, you can even go ahead and calculate the adhesion strength of this particular. This is, I think it is probably a locate dielectric film on a substrate. So you can calculate what is the adhesive strength of this locate dielectric film onto the substrate. Okay. So you can do not only for higher loads, you can also do at smaller loads. So the lateral force sensor have much higher resolution. So if you wanted to understand the friction characteristics, you can also do that. And then you can also do it, this is done along a line. If you do a raster scan, you can remove material over a specific area. You can calculate the wear volume. And so you can use it for tribological studies. Okay. So finally, I would like to cover something on the high temperature. For high temperature application, the same similar setup works very well. So, but there is a change that the transducer need to be protected from the heat conduction. So there is a spring that kind of takes the heat and dumps into the material, and also there is the coolers, water cooling system, and that kind of takes the heat away from the transducer as well as from the stage. So we don't want to this heating stage that I'm showing over here. The heating stage is capable of going up to 1000 degrees C. So you need to somehow protect the system. So we have a kind of a water coolers just around the transducer as well as the specimen stage that kind of isolates the whole thing and then prevents the heat flow into the rest of the system. Okay, and with this we can with this I think now the 1000 degree option is available, I believe, or maybe available soon. But right now we can do up to 800 degrees C inside the SEM, and then you can do very high, and then the stabilization time is very less. We can do within 30 minutes, and you can have about 30 degree per degree, say 30 degree per minute ramp rates. Okay, so in this particular case, this is a nickel-based superalloy. I think the demo video that I'm going to show, it is also going to cover that in details, but I'm going to show this particular video to show the deformation, how this happens. This is done at 1000 degrees C. Okay, this is done at the Bruker lab. The low displacement response, the linear response, elastic response, and then you start to have this plastic deformation, where you can see this shear happening. Okay, and then, yep, very high deformation. And you can see that at 45 degree, the shear plane, and when you can unload. Okay, so you can do this at 1000 degrees C. So that's pretty useful. So if you wanted to understand the mechanical behavior of materials at higher temperature, this is done inside a vacuum and inside a SEM. So you can do that directly, and then you can get this video and do direct structure property correlation very nicely. Okay, so in this particular case, I'm comparing the deformation behavior from room temperature to 400 degrees C to 600 degrees C. You can see that how the deformation 2000 degrees C. The deformation, you can see a lot of shear bands, very less shear band in room temperature. At 600 degrees, a lot, but at 1000 degree, it is very different type of deformation. Okay, so this particular case is for experiments done on silicon. This is very interesting. Silicon, you can see that kind of a ductile to brittle to ductile transition. Because at room temperature, most of the deformation mechanics of silicon is through phase transformation. And as you increase the temperature, the phase transformation can be suppressed, and the plastic deformation through dislocation will get activated. So that is why you will have kind of a brittle kind of a behavior at room temperature. You can see the cracks forming on the surface. As you increase the temperature, you will be more ductile, but because the plasticity is promoted by the dislocation motion rather than the phase transformation. So in fact, you can measure the hardness, and if I don't have the plot here, I think one of those, yeah, I have the plot here. You can see that the hardness increases as a function of temperature up to some temperature, and then it decreases. When you heat a material, you will expect the plasticity to increase. But in this case, basically, a hardness increase means the decrease in plasticity, and then there is increase in plasticity. So the reason for is basically the two competing mechanisms that I talked about, the phase transformation from room temperature to up to certain temperature, where the phase transformation is the dominant mechanism, and above certain temperature, the dislocation-based plasticity becomes more dominant. Okay, that's why you have this. So with that, I'm going to stop it here, and I'm going to go play the demo video. And after the demo video, we can go for a question answer session. So let me play the video.
Hello, and welcome to today's virtual demonstration on high temperature testing using the Isotron PI89 Nanomechanical Testing tool. And today we're going to be doing pillar compression of Rene N5 superalloy at 1000 degrees C. My name is Eric Kinsella, and together with my colleague Sanjeet Bhowmick, we prepared this virtual demonstration for you. Let's start with an overview of the instrument, the PI89 high temperature nanomechanical testing system. This is designed for use inside of a scanning electron microscope. So here you get particularly good synergy for high temperature testing, where the vacuum environment will help to protect your samples from oxidation during the thermal cycle, as well as getting high resolution imaging from the scanning electron microscope, which allows you to observe the deformation mechanisms in real time and correlate it to your mechanical data. This makes it ideal for a variety of applications where they're concerned about extreme environmental performance of materials, especially because the nano to microscale sensitivity of this device allows you to focus on particular parts of the microstructure of an individual material or component, such as weld zones or grain boundaries, for instance. The way the system works is that it uses resistive heaters that are independent for both the tip side and the sample side. Both sides are under independent feedback control as well. And this allows for a very stable temperature set point that will also be well thermal matched between the two sides. And this is very important for minimizing drift during the test. On both sides, we also have thermal breaks behind the heaters, preventing heat flow out from the region of interest into the system, which will cause drift. We also use water cooling to extract any latent heat that gets through the thermal breaks. This system requires the use of the XR high load transducer because of the extra mass of the tip heating option. Here's a real life picture of how the system looks like. On the right-hand side, you'll see the transducer with the probe heater mounted on the end of it. This probe heater has leads for the temperature sensor and the heating, and on the end of it, you can see the probe that is threaded on. So these are quick and easy to remove and change out probes and continue testing. On the left-hand side is the sample area. We have the translation stages, and these are mounted to this dovetail piece, which the whole thing can slide, allowing you to set the length from the transducer with ease. On the front of that, we have the sample heater. We've got the water cooling coming in to the chilling block behind the sample heater. And on top of the sample heater, we have a sample mounted, complete with a clamp. And we'll go through some of these with more detail in the coming up slides. This system is also compatible with the rotation tilt stage if you wanted to add that as well, giving you more control over your sample positioning relative to the tip. This is the sample heater. It's a resistive heating element and has an integrated temperature sensor, both for monitoring the current temperature, but also for controlling the heater output. The central region is where the sample sits. It's about 7 millimeters across. You want to keep your sample as flat and smooth as possible to ensure good temperature conductance from the surface of the heater into your sample. There's an integrated thermal break at the backside to prevent heat from leaving the heater area and traveling back into the system. And this is one example of a sample mounting clamp. We have another version. This one is called the Horseshoe. It uses those 3 screws to tighten your sample against the heater and give good machine compliance. This is how the sample heater looks like assembled together with the sample and the Horseshoe clamp on top. The 3 screws are threaded in to hold the sample tight against the heater below. And the left-hand side is what's going to be mounted towards the top of the pico indenter. So you can see that it's open, allowing for a viewing window from looking with the electron beam from above. Typically, testing is done at a tilt of 10 to 20 degrees to allow good visibility of the sample. This is the other type of sample clamp, which is the finger type. Whereas the Horseshoe works really well for flat topped samples, this one's more adaptable because the fingers come in different lengths. And it also contacts with less of the surface of your sample if that is something that you desire. This is the probe heater. It also uses a resistive heating element and an integrated temperature sensor and an integrated thermal break to prevent heat from leaving the tip and moving back into the rest of the system. You can also see that there is a metal disc, which is an infrared shield to block infrared radiation from heating the transducer housing. You can see that the tips are threaded on and off of the end of the probe heater, so they're exchangeable. This is very important because probe wear at high temperature testing is always a concern. The high temperature aids chemical reactions that occur between your tip and your sample. In this case, we're using a 20 micron diamond flat punch, which can work very well in vacuum. With the sample mounted to the heater, we just need to attach the heater to the system. So you slide the two interlocking dovetail pieces together, as so, and then you just need to tighten the set screw on top. Similarly, on the probe heater side, we just need to take the cup on the back of the tip heater, slide it over the square nut attached to the shaft on the end of the transducer, and tighten it down with a set screw. So quick and easy for exchanging. And here's a low meg SEM image of the sample, the horseshoe clamp, and the tip together. You can see how the viewing angle works with the opening at the top of the horseshoe clamp, allowing you unobstructed visibility of your sample area. Those little black dots are locations for pillars. And then you can see how the tip comes in from above in order to compress your pillar of choice. Here's a much higher magnification view of one of the pillars from the superalloy. This was made by focused ion beam machining. So first you have to make a large cutout using a higher beam current to remove enough material around the pillar so you have good visibility of the entire height of the pillar during the test. Then you want to come in with finer currents to refine the shape of the pillar. So here we're using a square cross section, and each side is tilted in 2 degrees to remove the natural taper from the FIB process itself due to redeposition of material as you're cutting it away. These pillars are 6 microns across and about 16 microns tall. This is a good aspect ratio to use to avoid buckling if the pillar is too tall, or barreling if the pillar is too short. You also want to choose a tip that's a little bit bigger than the pillar to allow you to make good contact without blocking your line of sight. TriboTC is our software control interface for the temperature. This allows you to set the probe and sample set points independently, as well as control the PID gains on the feedback loops on both of the heaters independently. Here we're watching the ramping from 400 degrees C up to 1000 degrees C at a speed of 16x sped up. The original temperature ramp rate was 100 degrees C per minute, which is very fast. You can see that the ramping is very stable. You can also take this temperature data and output it to a usable format for later analysis. Now we've reached the 1000 degrees set point, and we're going to go back to looking at the pillar test. This is a still image of the pillar at 1000 degrees C, and you can see a little bit of oxide formation. But superalloys readily form oxides as a protective coating. So really that's actually quite impressive oxidation protection from the vacuum environment. Going to a video from our SEM lab, here's the hardware side of the temperature control, which is the Lakeshore unit. You can see how stable the temperature is at 1000 degrees C on both the sample and probe sides. This is the water chiller, which is used to circulate to those cooling blocks and extract heat from the system. We're running water cooling at just below room temperature. There's the overall setup, our dual BeamFIBSIM with a variety of attachments, including a Bruker eFlash EBSD detector. And the SEM is a Versa 3D from Thermo Fisher. The image on the monitor is actually a continuous acquisition, so you can see how stable the imaging is at 1000 degrees C, and there is no challenge capturing nice images at this temperature. This is the actual test. This is what we call a side-by-side, which comes from the analysis portion of our software. On the left, we've got the load displacement data, and on the right, we've got the SEM video. You can see initially we have linear and elastic behavior, and then the load displacement curve starts to curl over as we hit the yield point and get permanent shape change and plasticity in the sample. You can see that as you compress it, you get a diagonal slip step forming across the center of the pillar. We're able to achieve quite high plastic deformation. From the after-test image, it's clear that the plasticity is highly concentrated or localized onto just a few steps in the center of the pillar, forming a band. This can happen as slip steps are formed. They create a stress concentration, which makes subsequent formation of slip steps in the same area much easier. By comparison, looking at a pillar of a slightly different superalloy composition tested at lower temperature, here we see that the slip is a lot more homogeneous or distributed along the height of the pillar. Whether the higher temperature gives additional mobility to dislocations in the 1000 degrees C case and allowing them to avoid internal obstacles, or a difference in the internal structure of the pillars is an interesting question. We also did 1000 degrees C pillar compression on the bond coating, which is a protective outside layer that goes on top of the superalloy. As the material is compressed, you can see this oxide scale crack and flake off of the pillar. But underneath, there's still substantial plastic deformation, reaching about 14% true strain. The true stress, true strain side-by-side video is made using Tribology, which has more advanced analysis features built in. I also wanted to take this opportunity to briefly discuss another type of application, which is using indentation as a function of temperature rather than pillar compression. And the example case is the brittle to ductile transition of silicon, studied at 3 different temperatures: room temperature, 400 and 800 degrees C, and 3 different loads. And you can see that as you increase temperature, the deformation mechanisms change, which is a well-known phenomenon in silicon. At room temperature, we have lots of cracking, so the material is exhibiting brittle behavior. As we go up to 400 degrees C, the cracking is greatly reduced, but there are still some cracks. We can also see some evidence of plastic deformation from the pileup on the side of the indent. At 800 degrees C, the cracking appears to be completely suppressed, and instead all the deformation is accommodated by ductile means. And that concludes the presentation. I wanted to thank you again for attending and wanted to encourage you to reach out to both me and Sanjeet with any of your questions on nanomechanical testing. We'd be happy to answer and provide assistance with any experiments you might be interested in working on. I also wanted to point out that the PI89 is just one part of a whole suite of in situ nanomechanical testing tools that we produce, including the PI95, which is designed for use inside of a transmission electron microscope. We have models that support all of the different major brands of TEM. Then we also have the PI85L, which is a much more simple and smaller platform for doing in situ SEM nanomechanics, but does not have the great variety of options available on the PI89 or its high load capabilities. And so with that, I'll conclude.
Okay, so that's the video. And we'll stop here and take any questions. So over to you, Fatyan.
Yeah, thanks, Dr. Asif. Yeah, and also very good demo that we have that you just shown. So now we have a question from Dr. Sampath Kumaran. He says it's a pretty impressive and interesting, informative on the technological development of nanomechanical device, but he would like to know whether the indentation technique would give residual stress built up in the materials.
Well, yeah, indentation by itself, you can always, for example, if you have a residual compression or residual tensile stress on a material, And if you have a material which doesn't have stress, if you compare the three, you can always see the difference between one from the one which doesn't have a stress and the one which has compressive stress, or when you have a tensile stress. Low displacement curve itself will show clearly that difference. Okay, but what happens is, like, when you do this deformation, the deformation mechanics also changes. And for example, if you have compressive stress, it will pile up. When you have tensile stress, it will sink in. So when you try to calculate the harness remains the same. So there are ways to extract the residual stress, but you can qualitatively kind of do that. And in the olden days, like people used to use harness testing as a measure of way of measuring the residual stress. You can do that, but you got to be careful.
Right. Then another question that we have is, suppose we have done room temperature nanoindentation on one sample, can we use the same sample for high temperature nanoindentation?
Well, yeah, I mean, if you're not subjecting it to a higher temperature, because the samples, nanoindentation, you can do plenty of indents on the sample. So as long as you don't have any history, if you're starting from like room temperature to higher temperature, it should not be a problem.
Okay. Yeah. Another question from Shubha Panda is that can we calculate fracture toughness using indentation for brittle materials? Suppose crack occurs in Vickers micro indentation as well as in nano indentation, then which will be used for evaluation of fracture toughness?
Yeah, for fracture toughness measurement, you need to measure the crack length, and then you need to know what the modulus is, you need to know what the harness is. So with the in situ SPM imaging, you can do that very nicely with our system. But again, like there are models that we use to measure the fracture toughness, has certain assumptions. So if you validate those assumptions, then your measurement is right. For example, the crack length has to be certain length compared to the width of your indents. So if you have that, then you can measure the fracture toughness. So again, like, you need to have some cautions and in interpretation of the results. So if you do it right, and if you can measure the crack length, and if the crack lengths are much higher than the size of the contact, you can make a pretty nice measurement of fracture toughness.
Great. Sure. Yeah, there's another follow-up question from Dr. Sampath Kumar, that the tribological studies that you have mentioned is done under dry conditions. Can it also provide friction data?
It can give friction data because we have both lateral transducer as well as normal transducer. We can measure the lateral force and normal force. We can get the friction data. You can also do it very low. When we did that, it was much higher loads. You can do it to lower load. So it may be just friction condition where you don't have any much of a plastic deformation. And under that condition, you can measure the friction as well.
Great. Okay. Sure. I'm not seeing any further questions though. Okay. So with that, yeah, we conclude our today's session. I would like to certainly thank all our participants for joining us today and sparing their time of from the schedule. Also, all the recordings of this webinar will be available at our YouTube channel. So that we'll be sharing the link with all the participants. So if anybody couldn't miss or their friends couldn't join us today, like, certainly we'll be sharing the link and they can listen back. Also, we have all the recordings of our webinars on our website as well, which is at industronnano.com. So if any of your spare time, yeah, feel free to visit, and you can listen more of the interesting talks that we have done, in the beginning of this year. So yeah, with that we conclude our session, and we wish you all Merry Christmas for the Christmas coming, and also Happy New Year. So stay safe. Yeah, have a good day ahead.
Yep. Okay.
Thanks.
Thank you, everybody. Okay.
Yeah.